So cool AI. Hi everyone. Thank you all for joining. So today we are going to talk about use of the free vulnerabilities in the Android kernel and a very specific use of the free bugs. So say you're in the kernel, you found some use of the free bug on some kernel object, but it so happens that the only code flow that touches the freed object is this one, is trying to take a Spinlock on it and then release the lock. So nothing touches the object inside the critical section and nothing touches the freed object elsewhere. So this is all you got. And the question we try to answer in this talk is, can this situation be exploited? And further, can it be exploited reliably and generically? And by generic, I mean like have the exploit work on multiple vendors and versions. So before we proceed, a bit about myself. My name is Moshe. Currently, I'm a security researcher at Paragon. Prior to that, I was a security researcher at JSOF, and this whole research was done when I worked at JSOF. I started with embedded security, and now in the past few years, I focus on Android kernel research, and I also hold a master's degree in computer science from the Hebrew University. So the plan for today is to briefly introduce a vulnerability in Android binder kernel driver, which have the property I just described. And then through this vulnerability, I share the full details of the exploitation technique, and then we also see a demo video on the Pixel 6. So the bad spin vulnerability, as I call it, is a race condition in Android binder kernel driver, which leads to a use of the free on the binder proc object. It is reachable from the untrusted app SE Linux domain, and it affects a wide range of devices. And it was closed last year on Android Security Bulletin of October 2022. So to understand the vulnerability better, we need to talk a bit about binder. So binder is the name of the framework Android uses for inter-process communication. So for two applications to talk with each other, it uses binder. And at the core of this framework lies the binder kernel mode driver, which facilitates message passing between one process and another. So if a process wants to talk using binder, it will open the dev binder or dev hardware binder device and issue ioctl commands to the binder device. And this device is accessible by all Android applications. So the messages that are exchanged through binder are called transactions. And the transactions can contain raw binary data and also zero or more objects, which are special from the point of view of the driver. So as the transaction passes through the kernel, the driver sees every object and translates it before it gets to the other side. Now, a special type of object is binder handle, which allows a process to share a handle with a peer. So it goes like this. Let's say you have a process A, which have a reference to a process C, and it wants to share this reference with another process, process B. So what it would do, it will prepare a transaction containing the handle object and will send it to process B. And as the transaction goes through the driver will translate this handle object and will create a new binder reference inside process B that will point to the same node as process C. So now process B, after he got the transaction, he can interact with the same node, for example, sending transactions to it. And now this object is the main player inside the bug, so we need to dig deeper on the actual translation code. So the translation is happening in two steps. In the first step, the driver is going to allocate a new binder reference object and insert it to the relevant data structure of the target process, so to the relevant data structures of the binder proc and to the node itself through some list. And then in the second step is going to take a ref count on the binder node to which this binder ref points. Now, if this second step fails, then the new reference is not cleaned up by the driver, and this is the root cause of the bug. So they don't check here the return value of this function, and they don't clean up this newly created reference. Now, normally this is not a security issue, because when the target process exits, so when process B exits, it will clean up all of its references. But it can become a security issue if a certain race condition happens. So if process B will call exit and will clean up all of its references before the object got translated for it, then it can lead to a use of the free situation. So it goes like this. We first set up 3 processes, A, B, and C, and A have a reference to a node in process C. A will share this reference with process B, but now B is going to call exit when the transaction is processing to it, with the intention of winning the race condition. Now, if the race condition is won, a new binder reference will be inserted to its data structures after its death. And this is a problem because the binder reference structure contains a pointer to the owning binder proc. So it will contain a pointer to binder proc B structure. So if this pointer is touched, we have a use of the free bug. So this pointer, actually, the driver did touch it. So when C calls exit, and by the way, we can do it anytime we want because we control all of these processes. So when C calls exit, it will release all of its nodes. And when a node is released, all of its references are traversed. So at this point, we will have a use of the free when the code tries to acquire a Spinlock on this freed binder proc and then release it. And in this vulnerable code flow, we cannot reach this bottom half of the code because we cannot have a ref def which is not null because process B is dying, so it cannot subscribe to a def reference. So what we have is only a Spinlock and a spin unlock on the freed binder proc, and that's it. So to summarize, the bad spin vulnerability is a race condition that leads to use of the free on a binder proc. And by the way, we win it 100%. So you can find the full details in the write-up. And the binder proc structure is allocated in the general purpose cache, kmalloc 1k, which is relatively quiet, so it increases the likelihood of successful reallocation. And a nice property of this vulnerability is that we control the timing of the use of the free. So since we control process C, we can call exit anytime we want and trigger the use of the free. So now we are here, we have a use of the free bug, which is only the spin lock and spin unlock, and we want to reach the ultimate goal of having a kernel read-write and bypassing KSLR, so from which we can escalate to root fairly easily. And we also want a generic exploit that can be easily adaptable to any lock offset, and that will work on multiple kernel versions and devices. And of course, we want a reliable exploit too. So when we face the task of coming up with an exploit to such a vulnerability, we face multiple challenges. So the first is that it seems like a very weak primitive on the face of it, like flipping a bit from 0 to 1 for a very short amount of time. So what can we possibly do with it? And further, if we want to exploit such a tiny race condition, then we should be aware of the fact that Spinlocks disable kernel preemption. So we cannot have a context switch inside a Spinlock critical section. And this also applies to the lock being in the spinning itself. And on top of that, the inner lock offset, so the field on which we have the use of the free, varies and changes between devices and versions. So we record some multiple values of this offset, and we want the exploit to be working on all of these devices. So what we assume to achieve that is, first, we assume a queued Spinlock implementation, which is the default on ARM64 since kernel 4.19. We further assume that the lock offset is divisible by 8, and you'll see where this assumption comes from. And we also assume that GFP kernel and GFP kernel account allocations are served from the same cache. So this was the case on all the Android devices I checked. So I don't know if it's a wide Android kind of thing, but it was true on the devices I checked, so I assumed it. Now, as an attacker, the game we are going to play here now is to create a type of fusion situation by reallocating the binder proc as some different kernel object that have a field that overlaps with this inner lock. And then we want to trigger the use of the free and have this field change in some interesting way that will benefit us to get a stronger primitive that we can better work with. And ideally, we want this change to be persistent or long-lasting, so we don't want to exploit another race condition. So to do this, we need to understand better how spin-locks are implemented in the kernel. And spoiler alert, this is more complex than what you might think. So Linux uses a fancier algorithm for its spin-lock implementation, which is called queued spin-lock. It is designed to avoid starvation and improve cache utilization. So the basic idea is that the lock maintains a queue of threads that wants to acquire the lock, and each CPU spins on its own accessible value. So if CPU 0 currently holds the lock and executes its critical section, and CPU 1 comes along, then it will place itself at the end of the queue and spin on its own accessible value, waiting for the lock to be released. And when CPU 0 finally releases the lock, it will signal CPU 1 that the lock is released, and CPU 1 can go ahead and acquire the lock. So this is the basic idea, but we are interested in the actual implementation details. So spin locks are 4-byte wide, and these 4 bytes are broken into 3 subfields. So we have the tail field, which is 2 bytes, the pending, which is 1 byte, and the locked, again 1 byte, which reside in the least significant side of this D word. So if all of these fields are 0, this means that the lock is released and ready to be acquired. And if the locked byte is not 0, it means that some other thread holds the lock. So let's see an example. And what you can see on the left is a pseudocode of the spin lock and spin unlock implementation. It's a simplified pseudocode because the original implementation contains like atomic operations, memory barriers, etc. But we are interested in the core logic of the implementation. So let's say we have 2 threads, one of them running on CPU 0, one of them running on CPU 1, and both of them want to access a shared resource that is protected by spin lock. And let's say that the lock is not acquired at the beginning. When CPU 0 comes along and enters the spin lock function, it will see.
But you don't have a handy, do you have a mobile phone or something in the lab?
No. So let's say CPU 0 comes along, it wants to acquire the lock. So it will see that the lock is all zeros. So it will set the locked byte to 1 and will continue executing its critical section. And now while CPU 0 executes its critical section, CPU 1 comes along, wants to acquire the same lock. So it will see that the lock value is not 0, so it will jump to the next if statement. So there it will check the tail and the pending bytes. So if either of them is not 0, it will immediately jump to the queue label, in which it will places itself at the end of the queue and will spin on its own accessible value. But in this case, it will see that the tail and pending are all 0, so it will jump to the optimistic spinning phase, in which it will set the pending byte to 1 and will spin on the locked byte until it becomes 0. Now, when CPU 0 finishes the critical section, it will call spin unlock and will set the locked byte to 0. At that specific point, CPU 1 will stop spinning and will set the pending byte to 0 and the locked byte to 1, indicating that it's now the owner of the lock, and will continue executing the critical section. Now, 3 things to note about this implementation from an attacker standpoint is that first, the spinning is done only on the locked byte until it becomes 0. After this optimistic spinning, it will set only the pending and the locked bytes and would not touch the tail bytes. And also, we want to avoid entering the Q label. So it turns out that if we enter the Q label with uncontrolled bytes, then we are going to get an uncontrolled memory corruption that will likely crash the kernel. So we want to avoid entering the Q label and stay with this optimistic spinning phase. So now we'll try to extract some useful memory corruption primitives off of this implementation. So the first primitive that comes to mind is the semi-increment primitive. So the idea goes like this. We will reallocate the binder proc as some object that has a field that overlaps with the inner lock and set this field to a value between 1 and hex FF. And then we will trigger the use of the free. So the outcome of this is that the lock will spin, will set the pending byte to 1. So we just increase this field value by hex 100. So it can be useful if this field represents, let's say, a length. So this might cause some overflow elsewhere, or it may represent some flags, but we didn't find a good instantiation of this primitive. So this brings us to the next primitive that we can think of. And the story we tell ourselves with this semi-decrement primitive is that the field that we are catching with is a ref count. So if we assume that, we will reallocate the binder proc as some object. We will increment the ref count to a value between 1 and hex FF. Then we will trigger the use of the free. The lock will spin, we'll set the pending byte to 1, just like before. And then we will increment the ref count until it reaches to hex 200. And by incrementing the ref count, I mean taking more references on this object. Now, when the ref count field got to hex 200, the locked byte became 0. So the lock will stop spinning. We'll set the pending byte to 0, the locked byte to 1 for a very brief moment, because the spin unlock will set the lock byte back to 0. So the outcome of all of this is that the object has hex 100 read references, but the ref count shows 0. So the idea was that we now will do another increment and decrement operation on the ref count. And hopefully on the decrement operation, we will get use of the free on this new kernel object that might be stronger and better. But unfortunately, this doesn't quite work for 2 reasons. So first, we need to find an object with a ref count at a specific offset that we control the lifetime and the number of references it has. And remember that the offset changes between devices, so it would likely not be a universal exploit. And even if we expand the search to more objects that are not in the kmalloc1k slab, then we risk with reducing the stability of the exploit. And the second reason, which is more serious, is that incrementing ref count when it is 0 is considered a bad operation. So many code flows are guarding against this and using an inc not 0 operation. And further, on older kernels, there is this config ref count full configuration, which converts every ref count increment to a ref count increment not 0 operation. So this is likely not going to work. So what about pointer corruption? So naively corrupting a pointer would not work either, because if we reallocate the binder proc as some object that has a kernel pointer at that spot, and then we will trigger the use of the free, we will likely fail because the tail and pending fields are likely to be not zero. So at the Spinlock function, we will jump to the Q label and we likely crash. So remember that for the optimistic spinning phase, we need to have tail 0, pending 0, and locked byte, which is not 0. So what about this idea? So we will reallocate the binder proc as some object. We'll set this object to a 4-byte value which only has a least significant byte which is not 0, like before. We will trigger the use of the free from a specific CPU. This will set the pending byte to 1 and the lock will spin. Now we will free this object from another CPU and the lock will still spin because when you free an object, the memory is not initialized. So the lock will keep spinning. And then we will reallocate as another object that has a kernel pointer at that spot. Now, if the kernel pointer has a least significant byte of 0, then the lock will stop spinning and will zero out the second least significant byte of this kernel pointer. So this brings us closer to the goal, but we still have a problem with this reallocation step because it so happens that the Android uses init on alloc kernel configuration, which means that every allocation is initialized to 0, even if it uses kmalloc. And of course, if it uses kzalloc or kcalloc, then the memory is initialized to 0. And this is a problem because the lock will see the memory being initialized to 0 before it will see the kernel pointer, so it will be released too quickly, so we won't get our corruption. So the solution to that was to slow down CPU 0 significantly using interrupts and win this tiny race. So we will have an interrupt triggered while the lock is spinning. So it will see the kernel pointer and won't see this memory being initialized to 0. And we do this using a technique adapted from Jan Horn article, Racing Against the Clock, in which he uses high-resolution timers to raise an interrupt on a specific core at a specific absolute time. So this actually works. So we have an idea for a pointer corruption primitive, but now we need to find some good objects to instantiate this primitive with. So for the first object, we need to have at our specific offset a 4-byte value with only least significant byte, not 0. And for the second object, we need to have a low half of a kernel pointer with least significant byte of 0. And further, we need to control the lifetime of this object. And remember that the offset changes between devices, so we don't want looking for different objects for every version. We want 2 objects to rule them all. So for the first object, I chose the TTY write buffer, which is very convenient because we can control its data from user space. So we can ensure that it has just a D word with all zeros but the least significant byte. And also it is allocated from kmalloc 1k and we control its lifetime. So to allocate this object, we call open on dev ptmx and then write to the resulting FD the buffer that we control of size 1 kilobyte. For the second object, an ideal object will be an array of pointers. So there are multiple places in the kernel that allocates an array of pointers, but I chose the file descriptor table, which is an array of struct file pointers. And this solves the offset fragmentation issue because this will work on any offset that is aligned to 8. And further, this object is convenient because we can access the target FD. So we know the FD number that corresponds to the pointer at that specific offset because this is just the offset divided by 8. So to allocate such an object in kmalloc1k, there are two ways to do this. So the first way is by forking from a process that has a maximum file descriptor, which is between 64 and 128. So in this case, a new file descriptor table in kmalloc1k will be allocated for the child. And the second way is by using the dup2 system call. So the dup2 system call duplicates an FD to another FD number that you choose. So if we invoke it from a process that has a maximum file descriptor which is less than 64, and the new file descriptor is between 64 and 128, then in this case, the file descriptor table will be expanded for this process and will be allocated in kmalloc1k also. So in our proof of concept, we choose the dup2 technique because first, it has less side effects compared to fork, and second, we encounter mostly offsets which are greater to or equal 520. So this translates to an FD which is greater than 64, so it was a perfect fit for us. But I still need to convince you that we can ensure that the least significant byte of this kernel pointer can be 0. So first I'll say that it's not necessarily going to be 0, and if the least significant byte is not 0, it means that the lock will keep spinning, right? It will not break out of the spinning, and only if it's with the less significant byte of 0, it will stop the spinning. So the idea is that we can use the dup2 system call to repeatedly change the kernel pointer that is placed in that spot. So we invoke the dup2 system call with a random FD. So we change every time the kernel pointer that it's there until the least significant byte becomes 0. So when it becomes 0, the lock will stop spinning, and we can also detect this situation. So if we repeat this enough time, like 16 times, it's more than enough to succeed with very high likelihood. So that's cool, and we got a primitive that can zero out the second least significant byte of a struct file pointer. And further, this struct file pointer is accessible to us from user space via a specific FD number that we know. So now we are here, we are getting closer. So what we want to do now is to figure out what we can do with such a corruption. So to do that, we need to understand from which cache struct files are allocated. So struct files are allocated from a dedicated pool in the kernel, which is called the filp cache. So each slab consists of 2 physical pages that are adjacent. So it have enough space for like 25 objects per slab. And the slab start address is aligned to 2 pages. So what this means is that after we corrupt the struct file pointer, we are going to likely be outside of the slab. So this situation happens when the start address is not aligned to 16 pages. And our goal is to land on an object that we control so we can fake a struct file and then later do some interesting things with it. So we chose again the TTY write buffer for the object that we control, and it is allocated from the kmalloc1k slab, which consists of 8 pages per slab. So what we want to do now is to shape physical memory so that at a virtual address which is aligned to 16 pages, we will have the kmalloc1k with an object that we control. And then after that, we'll have the filp caches. and we use file descriptor from these field caches for the dup2 technique. So our strategy for the shaping of physical memory is fairly simple. We will do a warm-up round by spraying objects in kmalloc1k and struct files to fill up any holes. And then we will repeatedly execute steps 2 and 3. So we will reallocate 32 objects from kmalloc1k. So this will create a new kmalloc1k slab. And then we will allocate 100 struct files, and this will allocate 4 new fill slabs. And we hope that the shaping will succeed. So after shaping, we have 3 possible situations. So first situation is that after shaping, we land on the object that we control in kmalloc1k, just like we wanted. The second option is that after corruption, we will land on another struct file. So this can happen if the field that we are using the dup2 from is placed in a virtual address which is aligned to 16 pages. And the third possibility is that after corruption, we land on some unknown page. So what we want to do in the exploit is to have some way to detect whether we succeeded or not. So remember that we have an access to the corrupted file descriptor. So we can, with some indirect operations, like extract bit from the corrupted file and see if they match what we expect. But we have to do it carefully because we don't want to dereference any pointer from this struct file, because otherwise we might crash in the unknown case. So this rules out like trivial methods of opening proc fd info file. So we need to do this indirectly. So for example, we have a method to know whether the fdget function succeeds on this struct file. So we have such an oracle and we know whether we succeeded or not. So if we succeeded, we just move on to the rest of the exploit, and if not, then we try again, do the shaping, do the vulnerability, etc. So now we are here. We managed to corrupt a struct file pointer, the secondly significant byte. And we also managed to land on a fake struct file that we control its contents. So what do we do with this? So we chose to call close on this corrupted FD with the intention of this memory location to be freed back to the slab allocator. And then we would get a use after free on a TTY write buffer, which is much stronger. So let's see what happens when we close a file in the kernel. So first it checks the count of the file. It ensures that it's greater than 0. Then it invokes the flush operation if this pointer exists. And then unless the fmod path bit is set, it informs any denotify watchers. And finally, it reaches the fput line where it decrements the field count and free the file when it reaches 0. So we are now faking a struct file, so we can easily make sure that the file count is 1. We can easily make sure that the fmod contains the fmod path bit. But this is more tricky because at this step we haven't break KSLR yet. So what we need here is a valid kernel address which points to null. And we need this address to work on multiple devices. So indeed we found such an address in the vmmap region of the kernel. So the vmmap region is like a region in the virtual address space of the kernel which contains an array of struct pages that basically describes physical memory. So this memory location is not KSLR, so it lies at a fixed virtual address, and we found some 8 bytes of nulls there. So we use this this virtual address. So we managed to skip all of this if condition and reach the fput line, where after a RCU grace period, the file-free RCU function would be called, and there this memory location will be freed back to the slab allocator. Now, a question that will be raised at this point is to which cache this object is returned, to the Philp cache, like the argument says, or to the kmalloc1k cache, where it was allocated in reality. So the answer is that the cache to which this object returns is determined from the virtual address of the object being freed, not the argument. And in case of a mismatch, the kernel just issues a warning and happily will return it to the kmalloc1 cache slab. So at this point, we have a use of the free on the TTY write buffer. So with one more step, we will reach our ultimate goal. So what we are going to do is reallocate this memory location with an array of pipe buffers. And why pipe buffers? Because they are useful. So first, they contain a pointer to a struct page that stores the actual pipe data. So by altering this page pointer, we can get read-write on this altered page. And also it contains a pointer to a global kernel data structure, the pipe buffer operation. So if we leak this pipe buffer, we can defeat KSLR. So what we are going to do now is to leak a pipe buffer. So note that simply reading from the TTY file descriptor would not work because the TTY driver copies bytes from the TTY write buffer to some output buffer, and we read from the output buffer. But we can like circumvent it with a simple trick. We can, so we will first allocate an array of pipe buffer, which is initialized to 0. We will then utilize the software flow control capabilities of the pseudo terminal, and we will issue an ioctl that tell him to stop emitting data. And then we will write zeros on the TTY write buffer. So it will write the zeros, but will stop, like the thread would block before it copies the data to the output buffer. Then we will write data to the pipe, and so a pipe buffer will be populated with our precious kernel pointers. And then we will resume the pseudo terminal with another ioctl, and at this point it will copy the data to the output buffer, and then we'll simply read it from the output buffer. So this way we leaked a pointer to a global kernel data structure, and we can like subtract a constant offset to get the kernel base, which defeats KSLR. And to get an arbitrary read-write to the linear mapping, we can simply fake a pipe buffer. So by writing to the TTY file descriptor, we can fake a pipe buffer and fake this struct page pointer. So if we have a kernel virtual address in the linear mapping, we can calculate its corresponding struct page pointer, then write the fake pipe buffer, and then by reading and writing to the pipe, we will read and write from this struct page. And this was, again, this was stable, but we wanted a stronger primitive to the whole virtual address space of the kernel. So we used the primitive we just gained to find our task struct and change the other limit to gain full read-write capabilities. And we also have a technique to bypass user access override, which is a feature in ARM. So at this point, we achieve our ultimate goal, which is kernel read-write, and we bypass KSLR. So just for completeness, at this point, we will like to disable SE Linux and run code as root. So on the Pixel 6, we override the enforcing variable of SE Linux, but on other devices there are other methods to achieve that. And to run cron as root, so in the Pixel 6, we just stole the cred struct of the init process, which runs as root. But again, other vendors, there are other ways to do this. And we checked our POC on 3 Android devices, the Galaxy S22, the Google Pixel 6, and the S21 Ultra, multiple Android versions and multiple kernel versions, and it worked on all of them. Our proof of concept achieved like 70 to 80% success rate, which is varies between devices, background activity, and this number could be higher, like with a better shaping technique and overall better engineering, but this was enough for us, for our proof of concept. So now we'll see a demo video. Because I don't have live setup here, you can see it's Pixel 6 running Android version 13. We will now compile the exploit. We will set up a reverse shell listener. We then execute lookup to see the logs from the Android application. We then open the bed spin app and click on the exploit button. Now the vulnerability works. It first finds the offset dynamically, and then trigger the use of the free, do the shaping. We leak the pipe buffer, and finally connect to us. So we are now root with the SE Linux disabled. Thank you. So to conclude, we started with a really weak use of the free bugs and escalated our way through fully working privilege escalation exploit. So I guess the message is don't underestimate the exploitability of your bugs and don't give up. Thank you.